For chapter 27, we are going to talk about active galaxies and how they relate to quasars. What are quasars? How do we find quasars? How do we know how far away quasars are? So we're going to start with how quasars were discovered. If we look at this image, it looks like two stars with the bright X pattern diffraction and bunches of galaxies in the background. I'm going to skip ahead and tell you a secret. The star in the center is a quasar 9 billion light years away. The one to the right is in the middle of our Milky Way galaxy. So how did we even figure any of that out? Well, shortly after World War II, a couple of astronomers purchased some surplus radar equipment in the 50s and pointed it at the sky, because they wanted to see, is there anything cool out there in the radio portion of the spectrum? And so since they discovered these stars that can't quite be stars, they called them quasi-stellar radio sources, quasar for short. So when you just look out, nothing distinguishes a quasar from a regular star. So Alan Sandage took the first spectrum of a quasar, and then it was Martin Schmidt, who on the left, who actually solved the puzzle of the quasar spectra. So what is that puzzle? Astronomers could not identify the emission lines. Remember, emission lines in the spectrum. Every chemical has its own characteristic set of lines, and so they couldn't figure out, what are these lines? And Schmidt realized that they had the same spacing as the lines for hydrogen, but they were incredibly redshifted. So the Lyman lines that normally are way down here in the ultraviolet were shifted through the visible all the way into the infrared region. And so that amount of redshift would suggest velocities around 96% of the speed of light. And so everyone just absolutely was astounded. So instead of quasar, scientists called them quasi-stellar object, QSO. So the first QSO for which a redshift was measured is, this picture that we're looking at. This is 3C273. And so the redshift for this quasar shows that the light took 2.5 billion years to reach us. So it is 2.5 billion light years away. It is still one of the closest quasars to our galaxy. So 3C273 is also one of the most luminous quasars that we see out there. Absolute magnitude of negative 26.7. And so you're thinking back to a couple of chapters ago and saying, well, the magnitude of the sun is negative 24, but the absolute magnitude of our sun is 4.83. So remember, the more negative it is, the brighter it is. Absolute magnitude is measured at a distance of 10 parsecs, so 32 light years away, well, 32.6. So this quasar is approximately 4 trillion times more luminous than our sun at visible wavelengths. So crazy bright. And we're going to come back and look at that quasar again. So one of the first questions is, do QSOs obey Hubble's law? Do the redshifts really mean that they are as close or as far as the redshift suggests? Because if the redshift is wrong, then they could be closer and therefore they would be not as bright. So how do we even tell if the redshift on this is correct? Well, we figure out if it's part of a galaxy. Because if the redshift of the galaxy and the redshift of the quasar are the same, then they're moving together and Hubble's law applies. So, in order to find out whether that was worked or not, we ended up having to use space-based observations, the Hubble Space Telescope, because it does not have so much light lost into the atmosphere. And so the Hubble shows us, these are 6 quasars with their galaxies around them. So a nice spiral, an elliptical, interacting galaxies, irregular galaxies. So yes, the quasar is in a galaxy. The galaxy has the same redshift as the quasar. Hubble's law applies. They really are as far away as they say they are. So this means that they are crazy bright. If you add all the radiation together from QSOs, visible, infrared, radio, all of those different wavelengths, they have total luminosities that are, hundreds of trillions of suns. They often vary on timescales of months, weeks. Sometimes they vary so quickly that it's just days. So what does that mean for us? Well, what it tells us is that they're very crazy small. So we have a galaxy, and if this galaxy suddenly turned on today, and star A is, a distance from the Earth, 100 light years. So 100 years from now, we receive the light from star A. And then, as the light from these other stars arrives at Earth, this galaxy gets brighter and brighter and brighter until the light from star C arrives. Well, since this galaxy is 10 light years across, it takes 10 years for all of this light to arrive at Earth. And so for 10 years, the galaxy is getting brighter and brighter and brighter and brighter and brighter. So if those QSOs get bright and dim on a cycle of, months or days, that means that the entire thing is, only a couple of light months across, or sometimes even light days across. Remember, it takes 8 minutes for light to get from the sun to us. So our solar system is only several light days across. So these quasars with, luminosities of trillions of suns are only as big as our solar system. Wow. So M87, this is the same one of the ones that we looked at before, and we'll look at M87 again. Huge jet coming out of here. And so we see the jet is sort of blue compared to the light from all those stars that's very yellow. And that's because the electrons on that jet spiral down the field lines. Remember, electromagnetic field coming out of a star? So we're going to come back and explain these jets in a minute. But those jets are traveling nearly the speed of light. And you know, the bottom three images, we've changed the orientation on the picture, but we can see the light, the galaxy and the jet, the quasar and the jet in X-ray, radio, visible light, so we can always see that the galaxy is crazy bright and the jets are emitting in almost all spectrum. So we've kind of defined how we figured out quasars. The next question is, what are quasars? And since I've already been talking for 11 minutes, I'm going to start a new video.